Flat roofs, or more correctly, roofs with very shallow pitches, are not new. This church, built more than 500 years ago, has a flat roof covered in sheets of cast lead, made by pouring molten lead over a bed of sand. The lead is not original, although cast lead can last well over 200 years. Towards the latter part of the 19th century, an alternative flat roof covering became popular. Asphalt is a natural material dug from an asphalt lake in Trinidad. It was often laid on a composite slab of steel beams encased in concrete. The lake asphalt was sometimes mixed with limestone aggregate quarried in Italy, France and Germany, which was naturally impregnated with bitumen deposits. In the 20th century, bitumen felt became a cheaper alternative to asphalt. It's a sheet material originally formed by saturating animal or vegetable fibres with bitumen, distilled from crude oil. The felt is built up in layers, each one bonded with hot bitumen. If one layer fails, the others should still prevent leakage. During the huge housing building programme following the Second World War, built-up felt roofs were widely used, especially on prefabricated housing systems. A typical 1950s roof was built from square-edged softwood boards. 2 or 3 layers of felt were usual, with the initial layer hot bonded directly onto the timber or fixed with nails. A reflective surface finish was often applied to protect the felt from solar gain and ultraviolet light. The lifespan of these roofs was often short. Differential movement and twisting of the boards frequently resulted in a torn membrane. In the 1960s and 70s, bitumen felt became very popular for all types of buildings because of its relative cheapness and ease of installation. Its life expectancy varied. Although many of these roofs are still functioning today, many failed prematurely due to poor installation or inadequate materials. In recent years, the quality and variety of materials has improved. At the same time, so has our technical understanding. Whilst modern flat roofs can still be covered in felt or asphalt, other materials such as plastics are also used. Although these materials can be very different in their nature and composition, once in position, they all have to cope with the same environmental conditions. Roofs must be able to withstand a variety of loads, including snow, wind, and people. Good drainage is essential to minimise the risk of water penetration. A shallow slope or fall directs the surface water to drainage points, which can be internal or external. Flat roofs are also subject to extremes of temperature. Problems of contraction and expansion can not only damage the covering, but also the deck and surrounding walls. The conservation of Highcliffe Castle required the replacement, like for like, of a number of flat roofs. Although the original lead covering was probably cast, modern milled lead, where blocks of lead are repeatedly fed through rollers, is being used as a replacement. The contract included the replacement of all the softwood timber deckings supporting the lead, as well as the lead itself. Lead sheet suffers from a high level of thermal movement, which can cause tearing, ridging and buckling. Damage can be avoided by limiting the size of each sheet. The thicker the lead, the wider and longer each sheet can be. At the top and bottom of each sheet, the deck is stepped to prevent capillary action and wind-blown rain penetration. At the sides, timber rolls provide a means of jointing the sheets and provide resistance against wind uplift. A loose slip layer separates the lead from the deck, allowing differential thermal movement. Ventilation beneath the lead sheeting is crucial if condensation and the resulting chemical attack is to be avoided. Ventilation is achieved by leaving gaps between the boards and ensuring that the slip layer is vapour permeable. Lead is a very malleable and flexible material. It's easy to cut and easy to shape. It can be easily dressed at normal temperatures. Only the most complex shapes need additional heat. Although lead is the most common metal used on flat roofs, it's by no means the only one. Copper, zinc and more recently stainless steel are all suitable for flat roofing. The slip layer here is a synthetic textile made from polyester. This comparatively recent material has replaced slip layers made from bitumen felt. In hot weather, the bitumen could melt and stick to the lead and deck. This bonding restricted thermal movement. The impervious felt also restricted the evaporation of any condensation which might have occurred underneath the lead. When the bays have been roughly shaped, they're placed in position ready for final dressing. Lead is a very heavy material. Even this comparatively short piece weighs about 20 kilograms. A variety of tools are used to shape and dress the lead. Nowadays these tools are made from modern materials, but they're still based on traditional designs. To avoid forming a ridge which could impede drainage and cause localised ponding, the bottom edge of the timber deck is rebated. The top of the lead is dressed into this rebate to create a flush surface with the boarding. The hot working of lead with a naked flame is not without danger. Windsor Castle, for example, is one of many buildings where carelessness has led to disaster. At an individual level, lead is a highly toxic material and lead workers must undergo regular blood tests.
Don't believe that he works that hard all the time.
Excessive bossing or working of the lead can lead to a thinning of the material and premature failure. This is a particular danger at complex details. Excess nailing of the lead restricts thermal movement. The fixing details depend on bay size, lead weight, roof slope and exposure. Accepted good practice is to fix the head of the sheet and the top third of the side roll using copper nails. Lead is a highly durable material protected by a naturally forming surface layer of lead sulfate. As it slowly forms, this patina can wash off, staining other materials below. This problem can be overcome by a smear coating of patination oil. Despite its general durability, lead is vulnerable to some alkalis and acids. Water dripping off a concrete surface or water running through mosses, cedar and oak shingles can all cause problems. Although lead is common in conservation work, modern roofs are more likely to be covered with continuous waterproof membranes, usually refined from petrochemicals. Nowadays, roofs also contain insulation. Its position can vary, and this has implications for the roofing components. Warm roofs have the insulation above the deck. In sandwich construction, they usually comprise a vapour check to prevent interstitial condensation, a layer of rigid insulation boards, and a waterproof membrane. This is probably the most common form of construction in the UK. In an inverted warm roof, the membrane is laid directly over the deck. Insulation sits on top of the membrane, held in position by some form of ballast. A separate vapour check is not required. In houses, insulation is normally laid between the joists. A good flow of air is needed to ventilate the cold void above the insulation to prevent condensation. A vapour check should be included to limit moisture transfer from below. At this regional shopping centre, the designer has selected a warm sandwich roof with an asphalt membrane. There are various ways of providing the falls. Here, a sloping sand cement screed has been laid on top of the concrete slab. Hot bitumen is used to bond the vapour check or vapour control layer to the screed. At upstands, care is needed to ensure its integrity. The vapour control layer can be made from various materials. Here, a polyester-based bitumen felt is used. The insulation must provide firm support for the subsequent layers and withstand the application of hot bonding materials. There are a number of suitable materials, including rigid foamed boards, mineral wool slabs, and even cork. A sheathing or slip layer separates the insulation from the waterproof membrane, allowing minor structural movement of the building and thermal movement of the membrane. It also helps dissipate localized pockets of trapped vapour. It's laid loose on the insulation with lapped joints. So this is a typical warm sandwich roof. The insulation is above the deck, hence the deck is warm, and the membrane will be laid over the insulation. Modern asphalts are a mixture of natural lake asphalt, bitumens, and fine and coarse aggregates. The solid blocks are heated on site in an agitator. A high temperature is required to melt the blocks. The specific temperature depends on the composition and purpose of the asphalt. When the material is molten, it's drawn off ready for laying. The thickness of the asphalt is related to the function of the roof. It's normally applied in 2 10mm coats. At this thickness, its weight is sufficient to resist wind uplift. Additional coats, possibly containing grit or fine aggregates, can provide a suitable surface for areas of traffic, such as multi-storey car parks. Because the material is applied in situ, its long-term integrity is very dependent on the skill and ability of the operative. However well the material is laid, its durability is also affected by extremes of temperature. Heat sinks, which prevent rapid thermal expansion or contraction, can be provided by a surface layer of chippings or paving slabs. Painted surface coatings are also available to help reduce the effects of ultraviolet light and solar gain. They're less effective than either chippings or slabs and require periodic renewal. Vertical surfaces should be primed to provide a good key for the asphalt. Where it's difficult to achieve this, well-secured metal lath may be required. Failure to provide a good key will result in movement, blistering and possible slumping of the asphalt. This can lead to water penetration. On all but the smallest of roofs, asphalt must be laid in bays. To provide a watertight junction where bays join, the asphalt is laid in 2 coats. This allows the joints to be staggered and overlapped. Asphalt is a hard-wearing and impermeable material. Its life expectancy should be at least 40 years if it's correctly detailed, specified and laid. Built-up roofs usually comprise 2 or 3 layers of bitumen felt, either hot or cold bonded. They were first used as a cheaper alternative to asphalt. Initially intended for industrial buildings, their use quickly spread to include residential and commercial applications. The bitumen is delivered to the factory hot and is stored in heated silos. It can be modified with polymers which alter its chemical structure, making it more pliable at low temperature and generally improving its flexibility. The qualities of the felt are directly related to the base fabric. Early vegetable fabrics have largely been replaced by synthetic materials which are rot-free. Glass fibre, or better still polyester fabrics, give increased strength and a longer life. The felt first runs through very hot bitumen, which saturates the fabric. The fabric is then squeezed through rollers to consolidate the impregnated felt and remove excess bitumen. It's then coated on both sides with cooler bitumen to produce roofing felt of the required thickness. Some felts are given a fine coating of sand. This stops the felt sticking once it's been rolled. The finished felt is run over water-cooled drums to reduce its temperature before rolling. The highly automated process provides good quality control and ensures consistency in the finished product. This industrial roof from the 1970s is being recovered as part of an overall refurbishment. The original built-up felt was hot bonded to 25mm fibreboard insulation. Unlike modern construction, there was no vapour check. Where the structure is dirty or dusty, a cold bituminous primer is sometimes applied to improve its bond with the subsequent layer. The structure here is profiled steel decking. The new specification differs from the original in a number of ways. These include thicker insulation and a vapour control layer to reduce the risk of interstitial condensation. The first layer is the vapour check or vapour control layer. It's bonded in bitumen, which provides a good bond, evens out minor surface irregularities and gives almost instant adhesion. The bitumen is delivered to site in solid blocks, which are heated in a boiler to a maximum temperature of 260 degrees. Higher temperatures create the risk of fire and can drive off some of the chemicals vital to the bitumen's set. The vapor check is a lightweight sanded felt. Its purpose is to prevent vapor from below passing through the insulation and condensing against the underside of the cold felt. Maintaining the integrity of the vapor check is essential in this type of sandwich warm roof. The detailing around edges and upstands needs particular attention to ensure the effectiveness of the vapor seal. In a sandwich warm roof, the insulation lies directly over the vapor check. The polyurethane boards are factory covered on one face with felt. The surface is lightly sanded to prevent the boards sticking together during transit. They're laid with staggered joints to minimise the risk of future movement tearing the felt. Some insulation boards can also provide the roof falls. They're often specially manufactured to suit specific roofs and are wedge shaped to provide the slope. On this roof, the slope is provided by the roof structure itself. Modern felts, unlike their earlier counterparts, are better equipped to cope with minor movement and can be fully bonded to the insulation. However, a partial bond is recommended where there's a risk of trapped water vapour or gases formed by a reaction between the bitumen and certain insulation boards. One method of achieving a partial bond is to use a perforated felt laid loose over the boarding. As the underlay is unrolled, it squeezes out excess bitumen and pockets of trapped air. Spot bonding with the insulation board should only occur through the perforations. Partial fixing can be achieved through other methods. In a cold timber roof, for example, the first layer of felt can be nailed to the timber deck. Unlike ash felt, built-up felt roofs don't have enough weight to resist wind uplift. The final layer in a built-up roof is known as the capping layer. To achieve a neat joint at the side laps, a weak wallpaper paste is brushed onto the felt. This prevents unwanted squeezed-out bitumen from sticking to the mineral surface coating. Once it's cooled down, it can be scraped off. The green mineral finish is just one of many possible surface coatings. It provides a solar reflective finish and an acceptable appearance. An alternative approach would be to use an ordinary heavyweight felt covered with a layer of lightly coloured stone chippings bonded in hot or cold bitumen. Promenade tiles can be used in place of the chippings, where there's a light pedestrian traffic. In some situations, usually where appearance is important, the top or capping layer of felt can have a thin surface finish of sheet metal. Suitable materials include aluminium, stainless steel and copper. Recent developments in technology have led to a number of new roofing systems. On this warm roof, the vapour control layer and insulation boarding are fairly standard materials. What is different is the membrane itself and the way it's fixed. The membrane is a single layer of PVC laid in large sheets and mechanically fixed to the profiled steel deck. The edges are heat welded to provide a watertight joint. No bitumens or other adhesives are necessary. This film has briefly examined the construction of flat roofs. Although recent developments have provided us with several new materials, more traditional flat roofing methods using lead, asphalt and bitumen felt will no doubt continue long into the future.